Good evening friends. Today we shall be taking up analysis of resistive networks, a computer aided approach using graph theory. So, we will be going back to the equations that we derived in our earlier lectures on graph theory. So, let us have a system of n plus 1 nodes and b number of branches. Then I can write the branch current vector as I1, I2 and so on, IB. Similarly, the voltage vector for different branch elements will be like this. Excuse me. If there is a voltage source, then we can write voltage source with a resistance R. Then we can show each element like this. This is E, this is current I, this is R and this is V, the element voltage V. Then E plus V will be equal to R into I. If E is connected in the opposite direction, then it will be minus E plus V is equal to Ri. If E is connected like this. So, we get minus E plus V equal to Ri. Thus, we can write Ek plus Vk equal to Rk into Ik, k equal to 1 to b. This is a generalized equation and we can write in a vector form E plus V equal to R into I, where R will be a matrix R will be having only diagonal elements R1, R2 up to RB, rest of the elements are 0. Now, this is a very simple equation using Ohm's law. Now, we will consider a loop L in a graph. I will call it if we consider a loop, then all the branch voltages in that loop, if we consider, then k equal to 1 to say BL, BL is the number of branches in that loop L. In loop L, then sigma Vk, k varying from 1 to BL will be equal to Rk Ik, again k 1 to BL. Now, if we apply the Kirchhoff's voltage law, states sigma Vk in a loop is equal to 0, agreed, which means Bf into V equal to 0. Vk, sigma Vk, if it is for all the branches and if we consider all possible loops, then I can take the loop matrix, fundamental loop matrix into V bar, that will be equal to 0. Now, using this, if in the previous equation we use this condition, then we find E k equal to sigma R k I k summated over k, or we can write in terms of the elements. After all, these are the elements in the loop. So, we may write B I k, okay, B I k E k, k varying from 1 to B L equal to sigma B I k R k I k. Basically, this refers to those elements which are falling in the loop, and B I k are the elements of that fundamental matrix. So, that takes care of those elements in a loop, or generalizing this B f, this is for all i's. So, B f into E will be equal to B f into matrix R into I. This is a very important equation. That we get in terms of the loop matrix B f. Now, this we could have got from the other equation also, B f into E plus, if you would have multiplied this by B f, and B f into V is equal to 0, that we have already seen, we could have got the same relation. Now, if you consider E L dashed as a algebraic sum of the voltage sources in a particular loop, in a loop L, then E L dashed is nothing but summation E k, k varying from 1 to B L. B L will be the number of elements in that loop. So, I can write E vector, E dashed vector as E 1 dashed, E 2 dashed, and like that E B minus n dashed. B minus n will be the number of independent loops, and that is equal to, or the fundamental loops, that is equal to B f into E. All right, because E 1 dashed, E 2 dashed, etc., these are nothing but the total loop voltage. So, we need 2B number of equations that is B equations for the network topology, for the interconnections, and B equations, B number of equations for element relations. To solve in a circuit, therefore, we require 2B number of equations. Now, for a DC circuit, we first of all solve the voltages and currents. You are given the network connections, the resistances, and value of independent source voltages, independent source voltages. These are the quantities given, that is, we know the interconnections, resistances, and independent source voltages. You are required to solve voltages of different branches, voltages of branches, currents of branches, and then branch power. And you have to check the summation of branch power should be equal to 0. This is Diligence theorem, which states that sum of the total branch power is equal to 0. So, we will have to verify this relationship. So, in the classical approach, we solve n equations for n nodes applying KCL, and that is sigma I k equal to 0, and for b minus n number of loops we apply KVL to compute the B branch voltages. Okay. Now, let us see how we can take care of current sources. Current sources can be equivalently represented by voltage sources. So, or voltage sources can be converted to a current source. Let us see their equivalence. You all know that you must have done it in Thevenin's equivalent and Norton's equivalent, a similar treatment. So, it is just a repetition of that. We repeat just for continuity. We take Gk as the conductance of the current source, where Ek is the voltage source with a series resistance Rk, and suppose this is minus, this is plus, this is the voltage V, same voltage V, so this is Ik, all right. So, we have got V equal to minus E plus Rk into I, which gives me I equal to V by Rk plus E by Rk. Again, I equal to Jk plus Ik, okay, equal to Jk plus Gk into V. So, if you equate, you find 1 by Rk is Gk. So, V can be written as also 1 by Gk into Jk plus 1 by Gk into I, where Gk will be 1 by Rk. I can equate these. Gk is equivalent to 1 by Rk. If I substitute here, I can rewrite this, and Jk I am equating with the other term. So, V by Rk plus E by Rk can be written as Gk into V plus Jk. That means Jk equal to E by Rk. Okay. So, you can convert one to the other. So, you have got V equal to minus Jk by Gk plus I by Gk. So, we define a matrix G, which will be G1, G2, Gb, where Gi is 1 by Ri. So, this is a conductance matrix. which is nothing but R inverse. Thus, we can write R inverse E plus R inverse V is equal to R inverse R into I. I have just taken the first equation, or even before that, this equation, rather this equation, I have just multiplied by R inverse both sides. So, R inverse E is nothing but G into E, they are all vectors, plus G into V is equal to I, okay, or G into E is equal to J. We write this term, that is taking the source voltages only, the equivalent terms, the source current vector J will be G into E equal to J. Okay. J is the vector of branch independent current sources. That will be having the dimension B by 1. So, we get J plus, you can write J equal to GV plus I, J equal to GV, if I take to this side it will be minus GV plus I. If I multiply both sides, multiplying both sides by matrix A, we get minus A times J equal to A G V plus A I. And what is A I? We have proved earlier, it is equal to 0 by KCL. So, it is A G V. Now, we come to loop method. Now, let us consider the fundamental loops. Let us consider the fundamental loops, that is B minus n number of loops. Let B minus n be M. Okay. Now, any loop, if we consider any loop V, we can write the equation, loop equation R1V I1V plus R2V I2V, etc., number of, depending on the number of elements in that particular loop, is equal to EV dashed, where EV dashed is equal to summation of the source voltages in a particular loop, summation of the source voltages in a particular loop. That is, if there are different branches having different sources, so in that loop you add up the source voltages. So, that is EV dashed in that loop number V. Okay. So, IJV, we write IJV equal to current in the resistor RJV, that is branch J in loop V. V is a particular loop, so we are considering any particular branch J and corresponding current as IJV. Okay. And if we write now I1 dashed, I2 dashed, etc. as the loop currents in loop number 1, loop number 2, loop number 3 and so on, we can write this equation R11 I1 dashed plus R12 I2 dashed and so on plus R1m Im dashed is equal to E1 dashed, where there are m loops, m fundamental loops, m is equal to b minus n. So, like this we will have Rm1 I1 dashed plus Rm2 I2 dashed and so on, Rmm Im dashed equal to Em dashed. Okay. Here R11, R22, etc., that is Rkk will be the sum of the resistances in the loop K, and Rkj is equal to Rjk is sum of the resistances common to loop J and K. Common to both loop and J and K will be the element Rjk, it is same as Rkj, all right. So, there are m equations and m unknowns, there is a loop currents. So, you can solve, you can write in the matrix form and then we can solve by taking the inverse of the matrix. The number of equations will be smaller. This is the most important advantage of this method. So, we follow the following steps. 1, number the circuit elements, take a real generator. A real generator means a voltage source with a resistance. A real generator is taken as an element, as a single branch, as a single element. By element we mean the branch. Next step, real current source is converted to an equivalent voltage source, an equivalent voltage source. That means, wherever there are current sources, you convert them to voltage sources and put it in the branch, and then select a tree from the original graph. We have already seen earlier how to select the branches of a possible tree by those transformation of matrices and selecting a particular set of nodes and elements. So, we select a tree from the original graph, this need not be a unique one, and then we arrange the twigs first, then the links. So, arrange the twigs first and then the links. So, we find out the fundamental loop matrix, find the fundamental loop matrix BF and number the twigs. That is BF you write in a partition form, BF which one should come first, you find out twigs and links, we do it right like this, twigs and links. Then we draw on the circuit, the branch currents in the direction of the graph. Normally, we choose the direction of the graph as the direction of the current through a particular element. In the direction of the graph branches. Then you write the system equation, solve for I1 dashed, I2 dashed, I3 dashed and so on up to IM dashed. Once you have got these currents, obtain I1, I2, I3 the branch currents and the branch voltages V1, V2 etc. up to VB. Then calculate power in each branch and then check whether this condition is satisfied. This is the Diligence theorem that has to be satisfied. Let us take up an example, then it will be clear. Let us have a circuit like this. This is 15 ohms, this is 15 ohms, this is element number 1, this is 100 volts, this is 10 ohms, this is element number 4, element number 6, this is also 10 ohms, this is also 10 ohms, this is element number 5, this is element number 2, value 20 ohms and this is element number 3. This is node 3, this is node 1, this is node 2 and this is reference node 4. So, we draw a tree, a graph we draw we can take number 4 as the reference node and I can take this as the tree. These are the 3 different directions. This is element 1, element 2, element 3 and then I will show the other branches of the graph, that is the links by dotted lines, and this is element number 6, this is element number 4, this is element number 5 and I have taken the directions like this. I will show the loops in this diagram here, which we will be referring to. The loop will be sorry, this is with the first link loop 1, that is the loop current as I1 dashed, then I take I2 dashed for loop 2 and the outer one I3 dashed, which will be taking number 6. They are corresponding to the links number 4, 5 and 6. I have shown it separately because it will be quite clumsy here. So, I wanted to be shown this to be shown separately. Now, number of branches is equal to 6, n is equal to n plus 1 is 4. So, n is equal to 3. So, number of fundamental loops will be 6 minus 3, that is 3, and there are 1, 2, 3 loops here. These are the 3 fundamental loops we have chosen. R11 will be R1 plus R2 plus R4. In the first loop, R1, 4 and R2, these are the 3 resistances. Earlier we had mentioned that the diagonal elements will correspond to the elements in a particular loop, the resistive elements in a particular loop, the sum of that. Similarly, now that comes to the values are given here 15, 10 and 20. So, that comes to 45 ohms. I am not writing ohms every time, the unit is same, a standard one. R22, similarly in loop 2 will be R2, R5 and R3. So, 2, 5, 3, again 15, 10 and 20, 45 ohms. R33 will be the third loop, that is 1, 3 and 6, 15, 15 and 10, that is 40. Now, R33 is 40. What will be R13? That will be same as R31. If there is any element common between loop 1 and loop 3, that is this element, that is 15 ohms, only R1. The element that is common between 2 and 3, between loop 2 and loop 3 is element 3, element 3 is 15 ohms, and R12 is same as R21 is the element common between 1 and 2. Now, the directions are opposite. So, these two elements will be negative, minus 20, because this loop current and this loop current they are opposing here in the common element 2. So, their value will be minus 20. So, let us now write with this the equations. Again, the voltages E1 dashed is equal to E itself. In the element 1, in the in loop 1, there is only one source, and the sum of the voltage sources will be just 100 volts. So, E1 dashed is equal to E itself, that is 100 volts. In loop 2, there is no source voltage. So, E2 dashed is 0. In loop 3, again E3 dashed, outer loop will contain this voltage. So, E3 dashed is also 100 volts. So, we get the equation like this. If you permit me to write these values in the R matrix, it will be 45, 45 and 40, R11, R22 and R33, then minus 20, minus 20, 15, 15, 15, 15. This is that R matrix into I1 dashed, I2 dashed, I3 dashed. We get the voltage vector E dashed, which is 100, 0, 100. So, by applying Cramer's rule, you can solve for I1 dashed, I2 dashed and I3 dashed. For example, I1 dashed will be the first column replaced by this. So, 100, 0, 100, then minus 20, 45, 15, 15, 15, 40. Determinant this divided by 45 minus 20, 15, minus 20, 45, 15, 15, 15, 40. So, this is I1 dashed. Similarly, we can evaluate I2 dashed and I3 dashed. So, after you have evaluated I1 dashed, I2 dashed and I3 dashed, we will find out the branch currents. We know the relationship between the branch currents and the loop currents. In this case, the branch current I1, if we refer to the diagram here, this branch current will be the loop current I1 dashed plus the loop current I3 dashed, they are in the same sense. So, both the loop currents will add up together to give the branch current I1. So, it will be I1 dashed plus I3 dashed. Similarly, I2 will be minus I1 dashed plus I2 dashed. This current is this loop current minus this loop current. Similarly, I3 will be this current which is opposite. So, minus I3 dashed and plus I2. So, I2 dashed I2 is minus I1 plus I2 dashed, I3 will be I2 dashed, sorry, I3 will be I2 dashed and I3 dashed, both will be opposite to this. So, minus of I2 dashed plus I3 dashed. I4 is I1 dashed, I4 is same as I1 dashed, I6 is I3 dashed and I5 is I2 dashed. So, after we have evaluated these branch currents, we apply the relationship that is V1 will be minus E plus R1 I1. V2, since there is no source connected, it will be just R2 I2. V3 will be R3 I3. V4 is equal to R4 I4. V5 is equal to R5 I5. V6 is equal to R6 I6. There is no voltage source connected in this. So, we have computed the voltages, the currents, and hence calculate P1, P2, etc. P1 is V1 I1, P2 is V2 I2 and so on, and then check sigma Pi. Now, if you solve these values of I1, I2, I3 and check this, you will get this is equal to 0. The algorithm is very quick, but how do you explain this to the computer? So, computer has to be given a direction in a very systematic way, so that it can handle a very large data set. When the network is having too many nodes and too many branches, then you have to give a systematic order to the computer to compute these matrices and arrange these equations such that the solution can be obtained very quickly, and we can use some of the relationships that we have already established in a very simple way. We will see that now. Let us consider I1 dashed vector I dashed is equal to I1 dashed, I2 dashed and so on. There are m loops. So, this is loop current vector. which is same as IL we studied earlier. Now, if you remember, okay, I will just quickly mention the relationship that we are going to use here, and we have already deduced it in our earlier lectures. If you remember, I can be broken up into two components corresponding to the twigs and links, and corresponding to the twigs it was shown it is QL into IL, and this is IL itself. So, IL can be taken out. So, it is minus QL and matrix identity matrix into vector IL, which is minus QL is again, if you remember, BT transpose and U into IL, and what is this? Nothing but B fundamental transpose, the total B matrix into IL. So, I is related to IL, the link currents, by this. Therefore, BF into E I can write as BF into R into I, okay, E is equal to R into I, which is BF into R. Actually, I should write matrix R to be more specific, into, now I am writing this BF transpose IL, okay, and this we are defining as R dashed. Okay. So, BF R, BF transpose I am writing as R dashed. So, this will be R dashed into IL, and what is IL is basically I dashed itself, is it not? I dashed is IL. So, I might as well write IL or I dashed. This is the matrix loop equation. Matrix loop equation. R dashed is known as loop resistance matrix. M by M. Okay. It is a symmetric matrix. That one can prove. Mind you, this is not same as R, it is different from R. R matrix will have only R1, or I can write R11, does not matter, R2 or RB, these are all zeros, whereas in R dashed they are not zeros. So, the steps are very simple. Specify the circuit elements in triplets, specify in triplets the circuit elements. That is K, I, J. This is element number, starting node and finishing node, and each element will also be specified by type and value. So, these three nodes, then type, that is whether R, L, C, etc., and then value. We will see how to take L, C, etc. into account. formulate matrix A. Then obtain a tree. Then rearrange the columns of A, rearrange A, exactly what we did earlier. Okay, that is rearrange the columns, first the twigs and then the links. Rearrange A, that is A twigs and A links. Then formulate vector E and matrix R from the data that we have already entered, and in the previous step after rearranging the matrix A, and then compute E dashed vector and R dashed matrix. E dashed is equal to BF E and R dashed equal to BF R BF transpose. So, solve next step, solve I1 dashed equal to R dashed inverse E dashed, then compute I from this BF transpose into I dashed. It is so systematic, and then compute V from this relation E plus V is equal to R into I, and then compute Pj equal to Vj into Ij, and then summation Pj check, that is same as V transpose I should be equal to 0. V transpose I is basically this sum. So, for the last example that we took, A matrix A 1 2 3, the elements are 1 2 3, these 3 elements form a tree. So, we have just taken as it is, and this is a relatively simple example. So, the connections will be 1 0 0. If we refer to the diagram, let me see the network that we took. Anyway, if you check the values 0 minus 1 0 0 0 1, then 1 minus 1 0 0 1 minus 1 and 1 0 minus 1. So, with the transformation, so that we get unity matrix here, we get after transformation 1 1 1 minus 1 0 minus 1 1 minus 1 0 0 minus 1 minus 1. So, this is nothing but QL. If you remember, we are trying to find out matrix Q from A matrix by transformations. So, this is QL. So, if you know QL, you know BT and hence BF. So, BF, if you remember, it will be transpose of this, that will be coming first and followed by a unity matrix. So, it will be 1 minus 1 0, then 0 1 minus 1 0, just put opposite signs and then transpose, you will get this matrix. So, 0 1 1 0 1 1, then 1 0 1 1 0 1, and then unity matrix 1 1 1 and then zeros. This is matrix BF, because BF is nothing but minus Q link transpose partitioned U. Therefore, E in our case it is E1, E2 up to E6, it is 100 and rest are all zeros. R is equal to R1, R2, R3 up to R6. The values are given, rest are all 0. So, it is like this: 15, 20, 15, 10, 10, 10. E dashed is equal to BF into E, which will be BF is this matrix multiplied by 100. So, I will not write all the terms, it will be 1 0 1 minus 1 1 0 and so on. You can complete BF multiplied by 100 0 0 etc. Okay. So, that gives me 100 0 100, okay, and R dashed will be BF R BF transpose. So, you can compute this BF, you know, 1 0 1 etc. Then you write R 15 20 15 and so on, the 6 diagonal terms multiplied by 1 0 1 minus 1 1 0 and so on, 0 0 1 is BF transpose. So, it is a 3 by 3 matrix. Okay. So, I1 sorry I dashed will be R1 sorry R dashed inverse, the inverse of this 3 by 3 matrix into E dashed, okay, where E dashed we have already computed E dashed as 100 0 100. So, whatever is the inverse of this matrix, there is the 3 by 3 matrix that we get, that multiplied by 100 0 100. So, that gives me I1 dashed, I2 dashed, I3 dashed. Once you have got this, compute vector I, that is BF transpose into I dashed, and BF transpose is known 1 0 1 minus 1 1 0 and so on, and that multiplied by I1 dashed, I2 dashed, I3 dashed. So, you get 6 values I1, I2 and so on up to I6. Okay. So, V you can compute minus E plus Ri, and hence P will be V1 I1, V2 I2 and so on. That will give you the branch power. Total sum of that will be equal to 0. Okay. So, sigma Vi II will be equal to 0. So, this you can check. Now, I have left the problem unfinished. I have just given you the hints how to solve it. You can try it yourself, you will get the result. Thank you very much. Good afternoon, friends. Today we shall be discussing about synthesis of RLC network. When we say synthesis, we are still restricting ourselves to two terminal network, that is one port network. Now, before we go to the synthesis, we will define some functions, special type of functions. Minimum function. What is a minimum reactance function? First we define a minimum reactance function. A minimum reactance function we get when an impedance function has got no poles on the imaginary axis, that is an impedance function having no poles on the imaginary axis. That means in ZS was in parallel with the capacitor. Okay. So, you have final ZS as a capacitor in parallel with that Z1s that is 1/4 ohm resistance and network like this, and then an inductor, and this one is resistance So, this is the structure of ZS. The number of elements required here will be more. You see, it is no more canonic in that sense, because we are getting a negative inductor in case of Bruni synthesis, we coupled it with a transformer. The number of elements there we got much less. Here it will be 1, 2, 3, 4, 5, 6, 7, 8. Nevertheless, this is easier to implement. There is no coupling involved. Okay. So, thank you very much. We shall continue with this with a few more examples in the next class.